Hello and welcome to our lesson on numbers and other bases. So there are plenty of real-world scenarios that require numbers to be in other bases or that use number and other bases. For example, time. Time it's a pseudo, like a kind of base 60 system of numbers. So think about when you're counting in time. If you were just counting by minutes, 1 minute, 2 minutes, 3 minutes, 60 minutes, you can go 61, so you can just keep counting your minutes in that base 10 system. But technically, when we get to 60 minutes, we have gotten to an hour. So every 60 minutes, we add an hour, right? So it's sort of like when we're in our base 10 system, we get to 9, then we carry over to the tens place, right, to get to that 10. Similar concept with time. Every time we get to 60, we add an hour, another 60, then it's 2 hours, another 60, then it's 3 hours, and so on. So it's kind of a pseudo base 60 system. We also have binary code. If you've done any kind of coding work or know people that have done it, it's binary, which means it's a base 2 system. Only zeros and ones are used in that system. Very necessary and useful. Many of our measurements also sort of operate in other bases. Again, think about just like counting from inches to feet. We could clearly just keep counting inches, 1, 2, 3, 4, 12, 13, 14, like it just goes on. I know I skipped a few in my count there, but like when we get to 12 inches, we've got 1 foot. And then when you get to 24 inches, then we add to a second foot, right? And then you get to 36 inches and it's a third foot. So you can keep using the base 10 numbers to count in inches, but if you want to go inches to feet, then every 12 inches you add a foot. It's sort of like a base 12-ish system, right? And then there are plenty of examples in ancient civilizations where other symbols for numbers are used and they operate in other bases. Like the Mayans, they used like a base 5 and 20 system. Babylonians, they used a base 10 and 60 system. The Romans used a base 5 and 10 system. Now, it's not likely that you've seen these systems of numeration before, but I'm sure we've all seen Roman numerals. So they use different symbols than we use in our system, and they also use a different base. So plenty of places where other bases are used. Now, when we're working with other bases, the rules are basically the same. And we're not talking about the Mayans, Babylonians, Romans, but just the digits that we use, but in other bases, the rules for counting are the same rules that we use in base 10. We only want one digit in each place value. Each place value represents a power of the base, just like it does in base 10. It's just if we change to base 3, then now our digits are all powers of 3 instead of 10. The powers will still start at 0 and increase by 1 with each place. And the largest digit that we can use in any place will always be 1 less than the base. So again, think about our base 10. We use the digits 0 through 9. So if I was operating in, let's say, base 5, then I'm using the digits from 0 to 4. Okay, so different bases, we have to restrict the digits that we're using. Now, if I'm looking at a single digit number, a single digit number is the same in any base. So single digit numbers are the same in any base. But if we have numbers or multiple digits in a number in another base, then those digits of the numbers with multiple digits, I didn't say that very well, but if we have, okay, let me just read what I wrote because I think I said it nicely in the writing. In bases other than 10, the digits of your numbers with multiple digits are read individually and the base has to be noted. And that still might not make a lot of sense, but I'm going to show you in just a second here. So let's try to explore numbers in other bases. Again, these are going to be numbers that use our same symbols, okay, but If we're in a different base, then our digits represent a power of that base and the symbols are limited, okay? So again, let's look at a base 5 for example. If we're dealing in a base 5, then the digits we're going to be using are from 0 to 4, so always one less than your base. Each digit in the place value of a base 5 number is going to represent a power of 5. All right, so 42 base 5 is actually the incorrect way to read that. I know it's tempting when we see this to read it the way we know it, but we're going to actually read this as 42 base 5, not 42, and this would be 103. What we want to say? Nope, we're going to say 103 base 5, and this we want to say 2,431, but we're just going to say 2431. So what I was trying to say in that one bullet, if we've got multiple digits here, we're going to read them individually and we're going to note the base. If it was a single digit number, no problem, we read it the same. So if I just had like 2 and then a little 5 here with the subscript, this means 2, and then this is a base 5 number. So the subscript is telling me what base I'm working with, okay? So 42 base 5 is how I'm going to read this number. So it is 4, 2, and then we're actually going to read that subscript as base 5. We have to say that base, if we're not in a base 10, if we're not in base 10, then you don't see the base written. It's implied because it's the number system that we all use. So if we're changing to something else, we need to make sure that we're saying that we're in that base. So 4, 2 base 5, again, we would read this as 1, 0, 3 base 5, and we would read this as 2, 4, 3, 1 base 5. So if we're reading these multi-digit numbers in other bases, we just read the digits individually and then note the base, okay? Now, what does it mean when we're looking at 4, 2 base 5? Again, if this is a base 5 number, it means that each of those digits represents a power of that base, so a power of 5, starting at 0 and working upward. So if it was 42 base 10, for example, then I know that this is 4 and times the power of 10, and that's to the first power, so and then the 2 would be 2 times 10 to the power of 0. So this would be the ones place, this would be the tens place, right? Same concept now, but now when we're in base 5, again, this 4, 2 base 5 represents 4 times a power of 5, plus it represents 2 times a power of 5. The powers will start at 0 and then just increase by 1. When I read this 103 base 5, again, 1 represents a power of 5, plus 0 represents a power of 5, plus 3 represents a power of 5. And those power of 5s start at 0 and they just increase by 1. And then 2, 4, 3, 1. So it's 2 times a power of 5, plus it's 4 times a power of 5, and then 3 times a power of 5, and then lastly 1 times a power of 5. Power of 5s will start at 0 and then just increase by 1. Okay? Now, what does that really mean? If we actually mathed it out, I just turned math into a verb. If we actually evaluated the expanded form, and I'll just pull out my handy calculator for that. If I put in 4, let me make my keyboard bigger, and actually multiplied it by 5 to the first power, and then added in 2 times 5 to the power of 0, that evaluation of that expanded form gives me 22. That's the base 10 value of that number. So the number that we think of as 22 is actually 4-2 in a base 5 system. So 4-2 base 5 and 22 in our base 10 system have the same value, which is kind of weird, I know, but this is how it works. So 22 goes here, and we can read that normally because that's a base 10 number. Let's go ahead and evaluate that second expanded form. We've got 1 times 5 squared. Oh, sorry, 5 cubed. And then we're going to add, oh no, I'm reading two problems at once. Let me do the second one. 1 times 5 squared, I was correct. Plus, technically, I wouldn't type this in because it's 0, but just so we can get it in there and you can see it all. Then we're going to add 3 times 5 to the power of 0. So when we evaluate that expanded form, we end up with 28. 28 is the base 10 value of that number. So once again, if we were looking at this base 5, number 103 base 5 is 28 in a base 10 system. So those two numbers have the same value, but because the digits represent powers of different bases, obviously they look different in the different bases. All right, let's do one more here. So we got 2, 4, 3, 1. Let's evaluate. So that's 2 times 5 to the power of 3. Plus, we have 4 times 5 to the power of 2, and 3 times 5 to the first, and lastly 1 times 5 to the power of 0. And so that ends up being 366. So again, 2, 4, 3, 1, base 5 and 366 are the same number. Obviously, they look different because they're in different bases. Those digits represent different powers or powers of different bases. And so they look different, but they have the same value. 2, 4, 3, 1 in base 5 is 366. Okay? All right, let's try this again, but this time let's look at a different base. Let's say we wanted to work in base 8. All right, your base 8 numbers are going to use the digits from 0 to 7. So it's always from 0 to 1 less than your base. If we're looking at base 8 numbers, then each digit in the place value of a base 8 number represents a power of 8. Okay, as soon as we change to another base, we read our numbers differently. Single digit numbers are the same in any base, so 7, base 8 is just 7, but it's base 8 now, so I want to make sure I state that. So I'll say 7, but I will say that we're in base 8. And again, 265, so not 265, but 265 base 8. And then not 30,421, but 30421 base 8. So when we're reading these numbers in other bases, we're literally reading those digits and stating that base. Okay, let's expand them out so we can figure out, like, really what is this number? All right, so when I expand this one out, obviously we've got 7 times 10 to just the power of 0. It's that single. And then 265 base 8. 2 is a power, oh not, I said 10 here. How dare I do this? This is base 8, so 7 times a power of 8, just the one power of 8. 265 would be 2 times a power of 8, plus 6 times a power of 8, plus 5 times a power of 8. Again, the powers of 8 will start at 0 and increase by 1. And then 30421. 3 times a power of 8, added to 0 times a power of 8. And then 4 times a power of 8, and then 2 times a power of 8, and I didn't make enough space, so I'm going to add on 1 times a power of 8, and then we start at 0 and work our way up with those powers, and so those are our expanded forms. And those expanded forms, evaluated, would tell us the base 10 value of that weird base 8 number that we're looking at. So let me get rid of all this. Well, the first one. Again, single digits are going to be the same. 7 times 10 to the power of 0 is still just 7. So 7 base 8, 7, same number. So when we look at those multi-digit ones where it's strange, so we've got 265 base 8 here. So 2 times 8 squared plus 6 times 8 to the first, and you're welcome to just put in the number when it's to the first power without putting that exponent in. And then we're going to add 5 times 8 to the power of 0, and if you just wanted to put 1 there because it's still 1's place, that's totally fine too. So we end up with 181. So again, 265 base 8 and 181 are the same value. They have the same value, they just look different because we're in different bases. Alright, and then let's do this last one. We got 3 times 8 to the fourth plus technically a 0 times 8 to the third, which if you wanted to skip putting that in your calculator, that would be fine because that's going to zero out. And then 4 times 8 squared plus 2 times 8 to the first plus we have 1. Again, if you just wanted to put the 1, that would be fine. So we end up with 12,561. So 30421 base 8 is 12,561. Those two numbers have the same value. So like imagine cupcakes, right? You're ordering cupcakes. If I ordered 12,561 cupcakes, that's exactly what I get. If I ordered 30421 base 8 cupcakes, it's the same order, okay? Alright, so let's try just a couple more without having to fill in the whole table here. Let's convert to base 10. So if I said convert this to base 10, that means I want to know what its base 10 value is. We're just going to expand it out and evaluate. So each one of these digits represents a power of my base. So 4 is a power of 6, and 5 is a power of 6, and 1 is a power of 6, starting at 0 and increasing, and then we evaluate. So we have 4 times 6 squared added to 5 times 6 added to 1 times 6 to the power of 0, which again is just going to be 1. So this is 175. So 451 base 6 and 175 are the same value. 7, 6 base 9, again both powers of 9, so 7 times 9 power of 9 plus 6 times a power of 9. Start at 0, work your way up. Evaluating this, we'll see what we're actually looking at here. So 7 times 9 to the first added to 6 times 9 to the 0. We're looking at 69 as our number. So 7, 6 base 9 and 69 are the same value. Right? And then lastly, we've got a binary one here in base 2, 1010, or sorry, 10110 base 2. So these are all powers of 2, kind of a longer expansion here. We got 1 is a power of 2 plus 0 as a power of 2. And I know these could technically zero out and be skipped, but I like to put them all there just so I have all my powers in order. Right, 1 is a power of 2, the next one is a power of 2, and then a 0 as a power of 2. So I've got 1, 2, 3, 4, all 5 of these. So we got 0, 1, 2, 3, and 4 when we put those powers in, and now we're ready to evaluate and see what we're actually looking at here. So I have 1 times 2 to the fourth. I'm going to add 0. I'm going to skip that in my calculator. Then I have 1 times 2 squared. And if you don't want to type the 1's in, that would be okay as well. And then I have 1 times 2 to the first, which is just 2. So this is a nice long coded way to write the number 24. So 10110 base 2, looks like a large number in base 2. It's really just 24. Okay? So hopefully you get the idea of expanding a number in another base or finding its value in the system of numbers that we use. Going to base 10 is relatively easy. If we want to convert from base 10 to a different base, it's definitely more challenging. So we're going to go back to our cupcake example. Let's suppose that business we opened up in that last lesson is flourishing, okay? But your box distributor went out of business. So you had to find a new vendor. You did, but now you're ordering boxes that look like this. It's a similar setup. You've got a cube, a square, a long, and a single. The single will still hold one cupcake, but this time the long holds just 4 cupcakes, the square holds 16, and the cube holds 64. And so these are all powers of 4. You got 4 to the power of 0 is 1, 4 to the first is 4. This is the one that's going to tell you the base that you're looking at. And then you got 4 squared to make 16, and then you have 4 cubed, which makes 64. So these are all powers of 4. Just keep that in the back burner. All right? Now, same rules as before for your packaging of your orders. So you're sticking to your efficiency rules. You always want to use the largest box that's possible for an order. Let me highlight those. Use the largest box that's possible. You can use combinations of boxes, but you don't want any empty spaces in your boxes. Otherwise, you're wasting space. That's not efficient. So let's suppose that you got an order for 3 cupcakes. How would you package that order? So 3 cupcakes. We're not going to the long box yet because there would be an empty space. So you're going to use 3 singles. Okay? Single digit number is going to be the same in every base, so that should make sense. If I had an order for 4 cupcakes, if I add just one cupcake to that order, then now I've got to go up to the long box because I want to use the largest box as possible, and those 4 cupcakes fit perfectly in that long box. So this would be 1 long box and 0 single boxes. Okay? 5 cupcakes. Can still use a long box here, but now I have an extra that's going to have to spill into the singles. So adding 1 cupcake there means I still have 1 long box, but now I have 1 single as well. Okay, if I had 15 cupcakes, I can't go here yet because I would have an empty space. So I could get, 3 of these? 3 of those 4 cupcake holders would be 12. And then I would have 3 left over to go into my singles. So I can use 3 long boxes. Again, 3 times 4 would be 12. Taking the 12 away from the 15 would leave me 3 singles left over. Okay, commas here. So you're getting the idea. And if you need to draw it out, right, you have 15 cupcakes. 1, 2, 3, 4, 5, 6. Sorry, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's cupcakes I could put in a long. There's another long box. There's another long box. And then here I have these 3 singles left over. So if drawing it out makes that easier for you to manage, that's fine. But you're going to see where it got some bigger numbers here. I don't necessarily want to draw them out every time, but you absolutely could. 16 cupcakes. Well, now I can go to my next box. 16 fit perfectly in the square. So that's going to be 1 square box, and then 0 long boxes, and 0 single boxes. Okay, so 1 square, 0 long, 0 single. 25 cupcakes. This would be the largest box I could use. So I'm going to still use 1 square box. Sorry, 1 square. And that would take care of 16. So if I have 25 cupcakes, I put 16 of them into the square box. That's going to leave me, 9 left over. So I can fit 8 into 2 of those long boxes. So if I put 2 long boxes in this order, then I get 8 of those. And so that leaves me 1 left over to go into a single box. All right, let's try another one. 63, we're close to that cube, but not quite there. So how many times can I get 63, or groups of 16 out of the 63? So let me use my calculator to help me out. 63, let me see, I got 16. I can still get 16 more. There's 31 left. I can still get 16 more. And then a 15, I can't get another one. So I can use 3 square boxes. If I use 3 square boxes, you can see I subtracted 16 3 times. That leaves me 15. So those 15 that are left over, how many long boxes can I use there? So long boxes are in groups of 3. I can, let's see, groups of 4. Take 4, take 4, and I could take 4 again. So I can use 3 long boxes. That would take care of 12 of those cupcakes and leave me 3 left over, and those 3 would have to go into single boxes. All right, now 70 cupcakes. Now I can jump to my cube, my 64 holder there. So I can go with 1 cube. So I've got an order for 70 cupcakes. I'm putting 64 of them in a cube, which leaves me 6. Now, I can't use a square box because 16 would leave space, right? I could still use a long box. I can do 0 squares, and then I can do 1 long box, and that would take care of 4 more of those cupcakes, and then I have 2 left over, and those 2 left over would have to go into singles. Alright, now finally I've got this last order. It's a lot of cupcakes, 250. Let's start with the largest box. I can get some 64s out of there. I can still get 64 out of there. I can still get 64 out of there, and I can't get 64 anymore. So that's 3 cubes that I can use. So 3 cube boxes. 58's big enough to get some squares, so let's see how many squares, which have 16, I can get out of there. Subtract 16, subtract 16 again. I can subtract 16 again, and then I can't anymore. So I can do 3 square boxes. And then let's see how many long boxes I can use. Those have 4s. So I can get 4 out of there. I can get another 4 out of there. So I can do 2 boxes of 4. So that's 2 longs. And then I got 2 left over. So 2 singles going here. Now what we're doing is we're fitting these base 10 numbers. These orders of cupcakes are in base 10 numbers. We're fitting them into the base 4 packaging system, which means we've converted from base 10 to base 4. So just to wrap your brain around that. What we said here is that 3 in base 10 is the same as 3 in base 4. Single numbers are the same. Here we said 4 in base 10 is 1 and 0 in base 4. 1 long box, 0 singles. What we've said here is that 5 in base 10 is 1, 1 in base 4. Or 15 in base 10 is 3, 3 in base 4. Or 16 is 1, 0, 0 base 4. 25 is 1, 2, 1 base 4. 63 is 3, 3, 3 base 4. 70 is 1, 0, 1, 2 base 4. And then 250 is 3, 3, 2, 2 base 4. So again, we took the base 10 and converted it to base 4. And think about the math that we did in that process. When we're converting to base 10, it's multiplication and addition. You're multiplying by those powers of 10 and then adding them together. So it should make sense that in this process of working in reverse, where we're trying to go from the base 10 number to, in this case, a base 4, we were dividing and subtracting. Now, it might not seem like division, but that repeated subtraction is division, just like repeated addition is multiplication. So think about that last one. I wanted to see how many groups of 64 were in the 254. So I could have divided by 64 and it would have said 3 with some left over, but that repeated subtraction, right, was the same as division. So hopefully the operations make sense, and at least the idea of packaging would make sense so that you can try to wrap your brain around going from base 10 to another base, or from another base to base 10, making those conversions back and forth. So you've got some problems in your assignment for you to practice, and I know it's a little strange, but if we really want to be able to teach our new learners how to operate in the base 10 system, we have to have a solid understanding of how it works. And if you have a solid understanding of how the base 10 system works, then you should be able to apply that understanding to other bases. So we're going to stretch ourselves a little here with the other bases. Again, it's going to solidify our understanding of the process, because the process is the same for all of the bases. So if we really thoroughly understand it, it's going to make it that much easier to teach our new learners. Okay, so again, you've got stuff to work on to practice, so give it a shot. And if you're struggling and you need some extra help, then please reach out, let me know. All right, guys, till next time, take care.